So hello everyone and welcome to our webinar, Optimize Energy Investments with Data-Driven Strategies. My name is Cynthia Selby and I'm on the Marketing Communications team here at Onset. And I'm going to give you a brief introduction and then I'll turn over the presentation to our speaker today, Greg Johnson. First, I'd like to share a little bit about Onset for those of you who don't know us. We are the company that makes the industry-leading HOBO data loggers, used all over the world for building performance monitoring, environmental research, and water monitoring. We've been making data loggers since 1981, and we've sold a lot of them, over 2 million so far. We have 120 employees located here in Massachusetts on beautiful Cape Cod, where we design and assemble all of our products. And we have a global network of dealers that serve our customers around the world. The webinar will run today for about an hour, and we will try to wrap up the presentation after 45 minutes and save the last 15 minutes for some questions. Please type your questions into that section on the Go-To control panel, and we'll get to them either during the presentation or during the last 15 minutes. We are recording the webinar today, and I'll be sending a follow-up email within a few days with a link to the recording so you can review it at your convenience. Now I'd like to introduce our presenter. We're very pleased to have Gregory Johnson, the president of Kilowatt Technologies, joining us today from Vermont. Gregory has over 25 years of engineering experience after graduating with a master's with honors from Tufts University in civil and environmental engineering. Kilowatt Technologies specializes in using data-centric, statistically driven methods to manage energy and environment in buildings. And their methods utilize thermodynamics and economics to identify financially justifiable decisions on energy consumption and capital purchase decisions. So now I'm going to turn it over to Gregory. Welcome, Gregory.
Thank you very much, and I thank you everyone for attending the webinar. As a little bit of further background of introduction, yes, I have a master's in civil engineering. I spent the last 25 plus years working as an environmental consultant, doing more of the traditional environmental type of practices of hazardous waste, and have been involved in Kilowatt now for the last 3 or so years. My partner in Kilowatt, he has a master's from Cornell, and his background is statistics and economics. Both of us are firm believers in the power of data, and that is how we started or developed the Kilowatt Technologies and the methods that we use to analyze and manage energy in buildings. Today on the talk, we will be going through a number of sections here. We will first give you some rules. Everyone has to have some rules. We will give you rules on how to collect data, smartly analyze it, and make financial decisions with it. And then we will go through a series of 4 case studies, a historic re-retrofit. No, that's not a typo. I'll get to that in a minute. Retail space, and then an HVAC Class A office building issue, and then finally a data center reconfiguration for a brand new data center. First, the rules of data collection for investment optimization. Number 1, collect data, lots of it. And you do this before you start acting. We start data we start the analysis of a building when we have more than 1 million records of data. Usually that takes between 3 and 4 weeks of time. Next is analyze the data smartly, and then act with financial efficiency in making your decisions. For collecting the data before you act, you have to have a structured data plan to do so. Or as my grandfather used to say, plan your work and work your plan. Always collect a very robust set of data. And finally, the 3 types of data that you should be collecting are thermodynamic data, i.e. what the environment is, the electrical consumption data or energy consumption data, and then finally the financial data of what it is costing to provide that environment to the building. Analyzing the data smartly is broken into three main categories. The first, understand what the thermodynamics properties of the building are. In other words, where the energy is going and what it is doing when it gets there. Second, understand what the occupancy of the building is doing. This is what the people and equipment and how they are impacting the building. A good example of this is we were working on a building that was originally designed to house a very large room of paper for paper files. They have then digitized all of that and moved all the paper files out, and now they have over 400 people working in there. They did not change the HVAC equipment at all, and obviously their environment was a little bit miserable. Lastly, determine how the various zones and uses of the building interact. The typical block data of what the zone blocks of a building look like are always looking good on paper, but most of the time they don't work very well in real life. To act financially efficiently, the first thing you do is, or what we recommend, is reconfigure the HVAC operational sequences based on your data. By doing this, you will remove approximately 75% or more of your HVAC energy consumption. Second, after you have taken care of or wrung as much energy out of the building as you can, the second step will be to reconfigure the HVAC equipment. We do not recommend purchasing HVAC equipment. We recommend typically reconfiguring as in ductworks, diffusers, things like that. And lastly, and only lastly, would you then attack your capital budget and, as necessary, remove equipment, preferably, or add equipment. And that is, in fact, what we found a very rare case. So in summary, first, collect the data before you act. Make sure it's a robust data plan that looks at the thermodynamic, electrical, and financial data for a given building. Analyze the data smartly to understand where the energy is going, what it's doing, what the occupancy are doing, and what the zones are. And then finally, act financially efficiently. By doing so, by concentrating on primarily the operating sequences, you can remove a tremendous amount of data from your, or excuse me, tremendous amount of energy from your building. By doing this, our practice, I guess is a better way to put it, our practice is to concentrate on the highest value, lowest cost items first when you attack a building's energy. For example, by installing data loggers, sensors to further the understanding of the resulting environment inside the building is a lot cheaper than to buy new mechanical equipment. So in order of rank here, we would first install data loggers and sensors and collect additional data to figure out what is going on. The second would be to work on the control system logic. The third would be on the control system hardware and configuration, and then and only then would we work on the mechanical system selection and configuration. By applying this, you can financially make decisions and wring tremendous amounts of energy at a low cost out of your building. By using a large-scale system to optimize your energy, the achievements that you will reach include you will eliminate or drastically reduce the occupant complaints. You will reduce the energy requirements to condition your building space. Your maintenance budget will be significantly reduced. This will include things like the HVAC contractors and other maintenance items to maintain your mechanical equipment. You will reduce your capital budget. We are reducing capital budgets in the buildings we're managing on the order of 20 or so, 20-25%. And finally, you will be able to identify shell issues inside their building and what are the most economic means of rectifying them. The best way to look at this is by comparing and contrasting a traditional thinking role with a data-driven thinking role. The traditional thinking is primarily how buildings are designed or were designed in the past, where there is a very low investment in controls, control logic, sensors, a very high investment in mechanical systems, and virtually no investment in the robust control sequences. This system takes a very short time to do. Depending on the size of the building, a mechanical system can be designed by a mechanical engineer or HVAC contractor in a matter of days, maybe a week. The data-driven method, in contrast, would be to look more at invest in the data acquisition and trending through sensors and loggers. Second, invest in the control sequences and systems. Third, reduction in the mechanical equipment, and then go on through identifying the shell issues. There was a question posted, what is an example of a control logic? This would be, for example, on a building automation system, look at it as most rudimentary is scheduling of when equipment starts. So when is your heat pumps, for example, in operation? Is it during occupied hours, or, as we have found, most of them are on 24 hours a day, 7 days a week, 365 days a year? Example number one. We're going to go through a number of examples. The first one is for Vermont Public Radio, or VPR. This is the main public radio station in Vermont. It has, we've been working on their main building. It's a 19th century building. It used to be an old horse barn, in fact. In 1995, it went through a complete overhaul with a custom designed HVAC system designed by an engineer, stamped by an engineer. Construction was overseen by an engineer. And unfortunately, the result was that the interior environment was extremely uncomfortable and uncontrollable. It had a very high energy cost, a very high maintenance cost, and they were beginning to have to replace all of their mechanical equipment well short of their design life. The first thing we do, again, is collect data, large volumes of data. In this case, because the building had gone through that major renovation, which included tremendous amounts of rework of interior space, but it didn't really include the rework of the electrical distribution, we actually used U12s and sprinkled them throughout the building, both on sub-panels and for environmental conditioning, and collected data there. We then went through and hardwired the sensors in. Again, the major points of data collection was the electrical submetering, looking specifically at the separate HVAC units and recording the actual realized HVAC operating sequences. The other area that we concentrate on is the thermal data, i.e., what kind of what is the resulting environment produced by the expenditure of energy. Once we collected the first wave of data, we then went through and did the analysis. The conclusions, the first one, yes, the environment was very undesirable. This is actually a very important conclusion to reach. I'm sure that most or all of us have heard that, well, people are just grumpy and you can't make them happy. What we have found is that while there is a small section of the population that is grumpy and you can't make happy, the vast majority, if they are complaining about environmental conditions, are actually suffering them. It is always very good to actually be able to say, yes, the environmental conditions in your office are undesirable. The second major conclusion is that all of the equipment was responding correctly. In other words, it was all working. Nothing was broken. What we also found was that the air handling system was in fact designed, was an excellent design, met all the requirements. It was, however, a complete lack of control systems in the building that was causing what appeared to be the majority of the problems, including the very high energy costs for the building. The actions that derived from the first phase included a complete control retrofit. The existing controls prior to us starting this project included a few programmable thermostats and some lever-driven thermostats. We have completely replaced all of those. We have hardwired in a large number of sensors throughout the building to continuously record the HVAC environment and what the HVAC equipment is doing. The result of all of this and the first wave of operating sequence modifications is we have essentially eliminated all of the complaint issues. We have reduced their total energy consumption for their building by 20%. And we have not asked them to purchase any new HVAC equipment. In fact, just prior to us getting involved, the HVAC contractor had suggested completely replacing all 5 pad mount units. To date, they have not replaced one of them. So what follows phase 1 is always a phase 2. In this case, again, we enhanced our electrical submetering, in this case using a whole stack of U12s. We expanded our thermal data collection, and finally we started incorporating the financial data, i.e. the utility bills, so we can cross-reference back to the submetering and the thermal data. What did the analysis of the second wave show? Something very interesting. It showed that the studio areas of the facility were rejecting tremendous amounts of heat. In fact, they never called for heat. They were always in air conditioning. It also showed that the areas, the heat requirements of the administration areas were overlapping very nicely with the heat rejection of the studio areas. And last but not least, it showed significant shell issues within the building. Since a picture is always worth more than 1,000 words, here is the footprint of the building itself. You have a performance studio on one end. This is actually 3 studios, studios A, B, and C. A music library. This is actually where now, because everything is digital, there is a series of computer servers here handling all of the music storage. Down in this corner is the administration area, and then up here is the development area. How the graphs are set up, the blue is the total minutes of cooling in a 3-month period from September 1 to November 30th. The yellow color, or yellowish color here, is the total amount of heating. What you see is the performance studio is 100% in cooling. The studios A, B, and C are 100% in cooling. The music library is, for all intent and purpose, 100% cooling. Remember, this is 12% of the total minutes called for, not total minutes of occupancy. In reality, this is about 45 minutes or so of time during this 3-month period. What you also see is the administration area and the development area is calling for 100% of the natural gas burn in the building for heating purposes. So what can you do with all this data? A lot of people collect data. We collect solutions. Here is what the existing is. You have 105 million BTUs of energy going into the studio areas to run all of the equipment. We're not going to change that. You have an additional 30 million BTUs of HVAC cooling, which is necessary to reject 66 million BTUs of heat that's built up in that area. In contrast, in the development administration area, you're burning 58 million BTUs of HVAC heat, and you're losing 55 of it through some significant shell issues. Specifically, when they went and renovated this building back in '96, they did a great job, except they left the 19th century windows in place. Furthermore, for whatever reason, they did not insulate sufficiently anyway in the development and admin area. So the heat is actually pouring out of the building at this end. Our solution will be to maintain the operations. We're not going to change that. There will still be a little bit of cooling applied, but the resulting 66 million BTUs of heat will be redirected into the administration and development areas, and we will have them fix the shell issues, which is new windows and new insulation. For all intent and purpose, we have just eliminated 100% of the natural gas burn to heat the building. This 12 million BTUs you see here, that's primarily to heat water to wash your hands in the bathroom. This is, in fact, the only building we have found so far where replacement of the windows and correction of the shell issues will actually have a significant financial benefit to the occupants. So this is it. This is what, again, what we have discovered and recommend. Reducting and redistribution of the HVAC with energy recovery, so we can capture the heat from the studios and eject it into the admin and development areas. Fix the windows, fix the shell issues. The minimum benefits or minimum results will be 75% reduction in natural gas. The latest analysis, we believe, are actually showing us a little bit higher now. 73% reduction in electrical cooling. And because we won't be using all of those pad mount units to cool, the mechanical systems will last a tremendous amount longer. Here are some pictures for you. This is the exterior of the building. Obviously, when the icicles are beginning to touch the ground, you probably have a heat loss issue. This is in the administration area. In contrast, here is a heat rejection unit that is cooling one of the studio areas. It's digging a hole in the snowbank. Another shot, this window is where the woman in charge of the facilities sits. Last time I saw her, it was during one of our cold snaps. She had on long johns, wool pants, wool socks, a sweater, and a scarf, and she was rather uncomfortable. The people down at the other end of the building in the studios was in short sleeve shirts. Second example, this is a retail space. It's the Outdoor Gear Exchange. It has a retail facility in Burlington, Vermont. It also has a web presence called GearX. 45,000 square foot retail space. Used to be the historic Woolworths. Then it got rebranded into another clothing store, and then GearX took it over. GearX is an outdoor apparel and equipment dealer. They have a very classic picture. They have 6 large rooftop units providing 6 different zones inside their building. The goals that we set for ourselves at the beginning of the project was to determine exactly what their HVAC capacity was, minimize their capital investment, and resolve what is becoming a rather uncomfortable working environment. Because it was retail, they wanted to keep people inside their building to buy more stuff, and it wasn't really happening. Again, first step, collect data. In this case, we collected electrical consumption data on the HVAC system to figure out what the realized operating sequences were, collect the data from each of the 6 zones to find the pattern of how they were operating together. The conclusions were very simple. They were not operating together. The 6 zones were operating completely independently with a few programmable and 2 mechanical set thermostats. These 6 zones were fighting more than Congress is. The result is that the zones were completely inconsistent with the uses. They had more than 3 times the capacity needed to condition their space, And we also identified something very interesting, and that was a thermal chimney effect during unoccupied hours. I'll go into more details on that in just a second. The actions that we developed from the first phase of data collection. First, put in controls. You can't run a building without them. Second, extended sensor array. These sensors were hardwired into the controls. This building also hosts now a nice collection of U12s in there to augment these sensors. In the very near future, some of those will again be hardwired. Then we will be moving the U12s to other locations within the building to, define the pattern of operation. The second thing is that we reduced the number of zones from 6 to 2. We also have completely removed 2 of the mechanical package roof units. They are locked out, tagged out. Eventually the electrician is going to come in and physically disconnect them. These will never be operated again. They are absolutely not needed. The result is that we first have stabilized the interior environment. Not only has the floor staff, but some of the folks that are coming in to buy stuff have stopped complaining. We have eliminated the conflicts, and we have, even with those 2 rooftop units, we still have more than 100% of the HVAC reserve capacity. Of course, after phase 1 comes a phase 2. In this case, through additional data, in this case particularly with the U12s, we have found that there is we need to have a ducting reconfiguration. What we're going to be doing is collecting the heat from the back area of the building and eject it into the front of the building where the door is where everyone enters. And by doing so, we will be able to remove yet again a 3rd unit. So we will cut their capital footprint of this building in half. We will also be retrofitting the damper system. What we found out was very interesting. This is a classic one of our data presentation slides. The green here is where the occupied areas of the building are. The various colored lines include, in this case, the exterior temperature, which was cruising around a nice comfortable 35 degrees. The zone temperature, where overnight the zone temperature was just under 70, which was the set point, and was holding very nice and steady. And then very interestingly, inside the air filter chamber on top of the roof, now this is a point sticking about 5 feet above the roof in the rooftop units, the temperature was a very nice and comfortable 65 degrees. That didn't make any sense. The only point where this heat could be coming from is from the interior of the building. So we then took a bunch of U12s down and stuck them into the diffusers inside the building and as a ductwork. And lo and behold, what we found is that entering the building during unoccupied hours was about 50-degree air. Exiting the building during unoccupied hours was 65-degree air. The only place the hot air came from was inside. The only place the cold air came from was outside. As soon as the mechanical systems were turned on, everything stabilized throughout the day. As soon as the mechanical systems were turned off, once again, there was cold air rushing into the building. What we have determined was happening was that the dampers used to seal or supposedly seal off the duct system are either broken, not working, or may not have even actually been installed. By plugging up this thermal chimney, we will be able to reduce another very large chunk of their thermal energy consumption. In fact, what we have found is that this was not occurring in just one of their rooftop units. It was occurring in all 7 of their rooftop units. So they are losing a tremendous amount of energy right through their roof every night. In summary, of the rooftop units, we're going to take their 6, reduce it to 3. We've already reduced it to 2, but we're going to drop another one out. Heat stages available, we're going to take it from 6 to 3. The amount of cooling, 12 stages to 5. A total reduction of 50% of the capital equipment, and a reduction of 67% of the installed capacity. And they will still have more than 100% redundancy in this system. Example number 3. The third example is a Class A office space. It's a 4-story, 40,000 square foot building. It's a heat pump, water source heat pump system. It has approximately 63 heat pumps that are working. When we were retained, the part of the third and the fourth floor was complaining of some significant comfort issues. They were actually a tenant. The owner occupied the remainder of the building. The tenant was experiencing 87-degree temperature inside the fourth floor of their office space during the summer. So yes, they were rather uncomfortable. We also very rapidly identified a very high turnover rate of heat pumps. They appeared to only be lasting between 5 and 6 years in some cases, which is a very expensive little problem. The goals set for the project: end the comfort issues, identify the heat pump failures, and reduce, if possible, the number of heat pumps to reduce the capital cost. We first, of course, started with a wide variety of data collection. In this case, we were looking for the realized environments across a subset of zones. In this case, with a heat pump deck, well, for this building, in fact, on the fourth floor, we looked at every single heat pump, but upon occasion, you can reduce the number of U12s and just look at decks themselves. We looked at the heating and cooling cycles, and more importantly, we looked at the very large upstream equipment. A lot of people that we have run across only look, in this case, at the heat pumps themselves. While heat pumps do consume a tremendous amount of energy by their operation, the majority of energy in a building is actually by the larger upstream units that most people ignore. One, because they're somewhat difficult to get to. The air exchanger was on top of the roof. It's kind of windy up there. The cooling towers are either on top of the roof or in inaccessible areas. And in this case, the boiler room, well, the boiler room was just very hot. The conclusions of our first level of data was that there was basically very little control, a very limited sensor array. There was no operating control sequences at all. In addition, we also found, once again, a major shell issue on the fourth floor. In the construction of this building, it was all built at the same time, but the first 3 floors were occupied, and the fourth floor was left vacant for a period of time until the tenant moved in. The tenant was in charge of finishing his fourth floor, and unfortunately, whoever finished it for him forgot to insulate the roof. The actions: install control upgrades to operate the heat pumps efficiently, place a sensor array throughout, a hardwired sensor array throughout the building, and then a limited duct reconfiguration. We also were able to develop a heat pump reconfiguration reduction plan. This is the fourth floor. The corner offices are where all the ties sit, but also where we're experiencing the worst realized environment. In fact, I believe it was this one that was seeing 87 or so degrees every summer day last summer. It was very uncomfortable for them. In contrast, the core of this building had some of the largest heat pump capacities of the entire building. To correct the issue, a contractor that was involved had suggested installing some additional heat pump capacity in these zones, and so you have 2 heat pumps in these nodes versus just 1. We came up with a different solution, and that is to extend the ductwork from the interior core, which was only operating at about 20% of its capacity, and provide conditioned air from the central core into the corner offices. The result of this was that we had eliminated all of the comfort issues within those corner offices without the addition of any mechanical problems, or mechanical equipment, excuse me. The second thing we are doing is, over a long-range plan, we are going to be able to, as these heat pumps die, reconfigure and combine these heat pumps circled in orange and reduce or eliminate a number of them. Currently, the legacy system has 16 heat pumps. We will be dropping down to 11 over the next 3 or so years, a difference of 5. We have achieved a 30% reduction in the mechanical capacity requirements of this building. The last example we'll be going through is a data center. Now, we probably all have data centers in our buildings. They are one of the largest energy density rooms or sections of your operation. In this case, we are back at Vermont Public Radio. They had a data center inside their main building, and in the start of a reconfiguration of that building, they were hiring new staff. They decided to move their data center to a new building that was immediately adjacent. They were also expanding their data center because of a greatly expanded web presence, which was becoming mission critical for them. In doing so, they wanted to design a data center that had, first, very low-cost cooling for operating expense reasons, and second, a very redundant, resilient system so they could keep their web presence up continuously. Using the data that we had collected from the old data center, if you will, inside the building, we were able to design a very robust system for them. First, we have decided to use and designed an outside air cooling with energy recovery. By using that system and the proper strategy and optimization of the equipment plan, we are able to maximize the value of energy produced. In this case, we set goals for ourselves of using 90% of all cooling using outside air. So only 10% was using mechanical cooling. In addition, we were going to recover all of that energy and use it to heat an adjacent space of the new building itself. To do so, we utilized a very high air volume cooling design. Specifically, the traditional design of a data center is that you use low volume air at a low temperature, and that will remove the heat from your computer racks. What we are utilizing, based upon a number of articles in the literature, is a very high volume air movement system. By pushing tremendous amounts of air across your computer racks, you are able to achieve the cooling necessary without a significant temperature delta between what your zone temperature requires and what the air moving across it is. The trade-off here is that you can use your investments on controls and sheet metal versus DX compressors. It also provides the ability for a much more resilient and redundant system, and it also allows you to do energy collection. The original design of the data center had approximately 75 kilowatts of energy going in per day to run the racks. That would have required a mechanical rejection of 250,000 BTUs. In addition, to heat this adjacent space, it was going to require 2.5 CCF of natural gas. Well, before they even started building this system, we got rid of this design and came up with this one. Again, same amount of energy going into power the racks. All of this energy was used to condition this adjacent space. At the time, we are now able to have the data center temperature held at 65 degrees, which is their design temperature. This space is held at 60 degrees currently. It's right now more of a storage area and a staging area for their data centers. As their data center goes through the next wave of expansion, the phase 2, the amount of energy coming in, of course, will increase, and it will raise this into a nice and comfortable approximately 65 to 68 degrees. Currently, there's absolutely no natural gas burned in this facility. In fact, we have had them remove the natural gas heaters because they are now completely redundant. So now, of course, I'm sure everyone's wondering, how does this work? Well, I would like you to meet the most fanciest snow steak in Vermont. This is the heat rejection unit of the data center. And as you can see, piled on top of it is the first snowstorm of the year. This is just early to mid-December. We had a dusting of a couple inches. Then during the Christmas holiday, we had approximately another 8 to 10 inches. Just after New Year's, we got another layer of snow. This heat rejection unit to date has never been on, probably will not be on, but is provided as a redundant portion of this system. Again, all of the energy consumed by this data center is currently being used to heat the adjacent space. A good contrast, again, this is the heat rejection unit from the data center, and this is the heat rejection unit from the same facility in their studios. Obviously, there's plenty of heat on this one. Not much heat coming out of that one. In summary, the rules for a data-driven investment optimization practice. Number 1, collect data before you act. Develop a very robust plan of a data collection and then work that plan. Collect thermodynamic data, electrical consumption data, and financial data. Second, analyze that data smartly. Don't use your eyeballs, use statistics. Understand the thermodynamics of the property. Understand how the occupants, the humans and computers, impact that. Understand how the existing equipment is configured that affects the occupants. And finally, act with financial efficiency. By doing it this way, you will be able to remove up to 75% of the energy consumption by your HVAC equipment. You will be able to also shrink your capital budget by removing HVAC equipment and providing a much more comfortable working environment. Or as this is one of our favorite quotes, Tex Johnson, he was a test pilot that flew the first 707 and much to the consternation of his boss, inverted it during the flight over to prove that it worked because there was 1,000 extra expert opinions in his words that called it wrong. One test is worth more than 1,000 opinions. By doing this, you can provide yourselves with a superior energy efficiency and provide your company with a competitive advantage. That concludes my presentation. Be glad to entertain questions. We have about 15 minutes left. Hang on. Let's see here. Just a second. We're trying to expand the question window.
Okay.
All right. We have a question here. High costs in relation to past Energy Star, what measure? I believe that that refers to the high cost of energy and how we are determining what the high cost is. Primarily, we compare all energy consumption to a baseline of the facility. We also look at the energy density, the amount of energy per square foot, and that will provide you with a gauge of how much energy, building by building anyway, is being consumed. We have seen buildings that are running at approximately $1 or so total energy, or excuse me, about $1.80 or so total energy per square foot per year, up to about $8 per square foot per year. Obviously, the bigger the number, the higher the energy cost density. Another question here is, please provide or describe the U12s and their installation. that, I think I will turn that over to an Onset representative in a couple minutes. Let me knock off a couple more questions, and I'll turn it over to him. There's another question. Can you recommend any print resources on data logging procedures analyses? Right. Yes, most of these seem to be more logger questions. Oh, wait a minute. How are you based geographically? And do you have a breakdown between preliminary study and detailed study, and what are the costs? We are limited only by the ability to pull data out of the building. Primarily, we will be able to reach out and touch any building that has an internet connection. Now, right now, we are concentrating in the northeast of the United States. As for the cost breakdown between the preliminary and the detailed studies, unfortunately, that has to be on a building-by-building basis. Some buildings are very well set up, and the initial cost is fairly minor, and others it takes a tremendous amount more work. What is the combination of loggers you use? Again, very building specific. We have a very large bag full of U12s. In fact, we have over 100 U12s in our inventory right now. We also use U30s and ZWs. Primarily, the first wave is with U12s because we move them around the building to figure out exactly what is going on, and then we transition to the U30s or the ZWs once we have established exactly what needs to be monitored and where. To sustain the game, do you provide design or implementation reports to analyze data after improvement? Yes, absolutely. That is the only way that you can sustain your energy consumption achievements. There is, because we bake things into the control systems, that is our primary target. As long as those control sequences are maintained and the occupancy and use of the building is maintained, it is relatively simple to determine if you are reaching your goals. However, you must come back and look at it again periodically. Otherwise, they will drift off and you'll be right back where you started from. Do you merge Onset sensors into commercial building automation systems or use sensors from the automation systems providers? Most of the building automation systems are proprietary systems, and you have to use their sensors. What we have done, though, in the past is basically combine them. So some buildings we work on have a building automation system, and we have augmented that with the Onset sensor and data logger packages. Again, another question on price, and unfortunately that is something we need to talk to you about your buildings. Do you find regional heating degree day data useful to compare to actual outside building monitoring? Bluntly, no. The amount of energy reduction and management that we are achieving typically completely swamps the heating degree day units. Also, if you flip back and take a look at the Vermont Public Radio section where it showed the various zones and the results, you will see that 3 of those zones were in cooling all the time, every day of the year, without fail. It was completely irrelevant to the heating degree day units. Typically, it is on a zone-by-zone basis will have, may have some impact, but primarily the amount of energy being pushed around a building will completely swamp degree day units. Do you have any comments on ways to handle and process data from a lot of sensors? Any helpful strategies? We've been developing that system now since 2008. It's going to take more than an hour. Sorry. In the Caribbean, heating is not a concern, but the high cost of utility bills and commercial AC for centralized units is high. how would approach or sell businesses or companies on energy optimizing in buildings? Oh, I see. I think you're asking how to approach the buildings to reduce their costs. While true, the first way to, or the first level that you have to attack on energy consumption is in fact the heating. Down in your area of the world, you don't have that issue. Primarily, I think the utility bills are going to speak for themselves. If you can go in and even reduce their total energy costs by 10%, that should really sell itself. Primarily, though, what we have found is that it is not really the energy savings, it is more of the reduction in capital footprint that is really catching people's attention.
Another great question.
How do you integrate the data from the portable units with the automation system? Again, the portable units stand alone. The automation system is proprietary. That comes down to the data regression analysis that we do and the reprogramming of the building automation system. To date, we have not been able to directly link the Onset systems to the building automation systems due to the proprietary nature of the building automation systems. What software do you use for regression analysis? I'm just a knuckle-dragging civil environmental engineer. You would have to talk to my partner who is in charge of the operations on that. He's been at the development of that since 2008. Next question, what comments do you have on using modeling data with actual operations? I ask because I see a disconnect for continued operation or verification. All right, I'm not exactly sure I understand that question. Primarily, we go into a building and model the data, model the thermodynamic and the energy consumption of the building as part of the determining the actual operations. Because of the sensor arrays, both either a temporary, and I put that in quotes, of the U30s or a hardwired system, we are able to continuously view that data. This data is collected on a continuous basis. With electrical consumption, you are looking at a 1-minute frequency data pulse. With environmental, you can stretch that out to 10 or 15 minutes, but it is a continuous operation. You cannot manage energy with a short snapshot of time. If you're going to manage energy, you need to look at it and collect data and analyze it 24 hours a day, 7 days a week, 365 days a year. You cannot just throw in a couple loggers, take a little data, and think that you solved the problem. When we work on buildings, primarily we need 12 months work on that building. It takes 2 to 3 weeks to start the analysis. It takes basically that long to start with 1 million records, and we can reduce the energy consumption starting from there. However, to squeeze the maximum amount of energy out of the building, you need to know, or you need to work it for about 12 months because of the seasonal variabilities. Would you recommend using an energy-efficient AC unit in a hospital, or would you retrofit the unit to work with solar panels? Well, good question. Unfortunately, it's not one I can answer right off the top of my head. It will depend on the operating sequence and the realized environment inside the hospital. It'll also depend on the specific type of AC unit that you have there. We are working on a number of buildings where we are actually going to be utilizing solar panels and converting office buildings and a number of office buildings to complete net zero. They will be actually generating more energy than their HVAC systems will be utilizing. Last, what type of marketing do you do to have prospects contact you? Well, you're listening to it. We also are doing a lot of direct outreach. We're even getting into the social media thing. Interestingly, this is an interesting topic just for my own self. Given the very interesting place that we find ourselves in history, with the newspapers basically going away, Newsweek itself has stopped publishing. We're getting our news and information from the internet, not necessarily from a fixed source. It has made the outreach a very interesting prospect here. Primarily doing these webinars, trade shows, publishing both in blog form and on the internet and in various online magazines. That is primarily how we're doing this. And now I will turn this over to Greg from Onset, and I have left him approximately 3 minutes to answer all of your data logging questions.
Thank you, Gregory. Appreciate you going through these projects today. It always amazes me how the data from our loggers can really allow you to affect meaningful change for your customers. The U12s that you mentioned, Onset has a number of standalone loggers. The U12s are a family that run from over $85 to about $133. They allow you to collect roughly 40,000 measurements per device, and some of the U12s have internal sensors for temperature and relative humidity and light, and there are external temperature sensors that you can connect to them up to 50 feet long to get temperature in hard to reach places. And the recording intervals can be set from 1 second up to 18 hours, so that you can get data at a very fine resolution or once or twice a day for measurements. And in addition to the standalone loggers, which operate, you connect them to a computer, you launch them, you put them where you want them to record data, and then you collect the data after your study period is done. We have loggers that can transmit data to the internet stations, and we also have wireless systems. And all this information can be found at www.onsetcomp.com, and we also have a dedicated team of application specialists to help answer your specific questions about the products.
They were up there at the top. And yes, that one.
Oh, resources on data logging, procedure analysis. Places that offer hands-on.
Onset also has a wide resource library that's with white papers and webinars similar to the one that you've heard today that we pre-recorded that get into techniques for using the loggers. Again, our application staff here is well-versed on the use and can help you through, or refer to you folks that we know that are more knowledgeable in specific subjects in terms of using the data from these devices. And once again, the presenter today was Gregory Johnson from Kilowatt Technologies. They're based in Vermont, and we've just put the contact information up on the screen. We'll be sending this information to all the registered attendees, as well as a link to be able to listen to this webinar recording again. And we want to thank everybody that signed on today. And we hope you found this to be useful information. We certainly did.